Howdy folks! Today we're going to look at more examples of implicit differentiation. This is the situation where you have some equation involving x and y. It might not just be y equals x squared or y equals cosine of x. It might not be a function of x. Nonetheless, it has a graph. This is the set of points in the plane satisfying that equation, and we can still find the derivative of y with respect to x. We do this by taking the derivative of the entire equation and using the chain rule judiciously.
Because I could find freedom on this canvas. There we go. There's absolute freedom here. And I think we're all looking for freedom.
Let's find the equation for the tangent line to the unit circle at these 3 points. 1/2 root 3 over 2, 0, 1, and minus 1, 0. So if you haven't seen it before, it's pretty nifty that the unit circle has this equation, x squared plus y squared equals 1. What I'm saying is, if you plot the points in the xy plane that satisfy x squared plus y squared equals 1, it'll be exactly the unit circle, like this. Okay? So if you look at the points a distance 1 from the origin, if you do the little Pythagorean theorem for the triangle, the right triangle, that radius, that hypotenuse makes, the Pythagorean theorem will give you that the equation is x squared plus y squared equals 1. Alright, so what are the points where we're going to find the tangent line? Here's the first one, 1/2 root 3 over 2. And then we also have to look at 0, 1. That'll be up here at the top. And then down here at minus 1, 0. So those are the 3 points of interest. Now to find the equation for those tangent lines, we're going to need to find the slope of the tangent line at those 3 points. So first, let's find the slopes. Well, to find the slope, we need to find the derivative of y with respect to x, the instantaneous rate of change. So to do that, we'll use implicit differentiation. That's the name of the game. So we're going to take that equation up there, x squared plus y squared equals 1, and we're just going to take the derivative of everything we see. We're going to take the derivative of the entire equation, like so. So I'm just taking the derivative of each term, term by term, and then we'll use this to solve for dy dx. Okay, first off we have the derivative of x squared. By the power rule, that's 2x. Next we have to take the derivative of y squared. That's the chain rule. The derivative of the outside function is the derivative of y squared. That's just 2y. But we need to multiply by the derivative of the inside function, which is dy dx. Y is the inside function, and then y squared is the outside function. On the right-hand side, we're taking the derivative of 1. That's a constant, so its derivative is 0. So now that we have this equation involving dy dx, we can solve for dy dx in terms of the variables x and y. So if you move the 2x to the other side, and then divide both sides by 2y, you'll get minus 2x over 2y. So I got that by solving for dy dx in the previous equation. And the 2's cancel, so we end up with just minus x over y. Not bad. Okay, and now to find the slopes at these points, we just need to evaluate at those 3 coordinates. So let's evaluate the derivative to find the slope of the tangent line. First, we're going to evaluate at 1/2 root 3 over 2. What do we get then? Then the slope, the derivative, will be minus the x-coordinate, which is 1/2, divided by the y-coordinate, which is root 3 over 2. So the 2's in the denominator on top and bottom cancel, and we're left with minus 1 over root 3. If you want to write that as minus root 3 over 3, I have no problem with that, but I'm going to leave it as minus 1 over root 3. Okay, and now we're ready to find the equation for the tangent line at 1/2, root 3 over 2, but let me quickly evaluate the other slopes that we'll need, just because we're right here using the equation. So let's see, when we plug in at x equals 0 and y equals 1 in the formula for the derivative, we have minus 0 over 1. That's just 0. So there's a slope of 0. The tangent line is horizontal at 0, comma 1. We get a slope of 0. That makes sense. Up here at the top of the circle, if you think about the tangent line at that point, that tangent line will be horizontal. It's going to have slope 0. So that corresponds to our calculation. Now what happens if we evaluate the derivative at minus 1 comma 0? Well, then dy over dx is going to be minus the x-coordinate, which is minus 1, divided by 0. Oh no. We did a bad thing. We're in trouble now. You should never do this, right? Division by 0 is bad. This is undefined. There is no well-defined slope. The derivative, strictly speaking, doesn't exist at this point, minus 1 comma 0. Why is that? Well, if we go back up to the unit circle, what would the tangent line look like? The tangent line at this point is going to be purely vertical. And a vertical line does not have a well-defined slope. So this is something that can happen with implicit differentiation because we don't have a well-defined function. So another way to say that is that the derivative doesn't exist at such points. All right. And we can see that the 2 points where this are going to happen are minus 1, 0, and 1 comma 0. Those will both have vertical tangent lines. The derivative won't exist there. And that corresponds to our formula. That's exactly where y is 0. And so our formula would be giving us something undefined. Okay, now it's time to find the equations for the tangent lines. Let's find the equation for the tangent line at 1/2 comma root 3 over 2. We just computed the slope of this tangent line via the derivative, and we got minus 1 over root 3. That's the slope at that point. And we also know that it goes through this point on the graph where we're taking the tangent line. So using point slope intercept form, the equation for the tangent line is given by the slope times x minus 1/2 plus the corresponding y coordinate. So there you have it. That's the equation for the tangent line. If you want to simplify, make it look a little prettier, you could write it this way. I don't know if it actually looks much better, but there you go. Now the equation for the tangent line at 0, comma 1. We know that the slope of this tangent line is going to be 0. We computed that just a second ago using the derivative. And it goes through that point 0, comma 1. So what does point slope intercept form give us? Well, we get this equation, but since the slope is 0, everything in that first term cancels and we just get 1. So we just get the line y equals 1. And that makes sense. That's the horizontal line up at the top of the unit circle. Now finally, what about the equation for the tangent line at minus 1 comma 0? Well, it's a vertical line. It doesn't have a well-defined slope. But vertical lines at a particular x-coordinate do have an equation. It's just given by setting x equal to minus 1. So that's the equation for the tangent line at that point.
So if you see little creatures around your house, help take care of them, because they're God's little creatures, and they're fantastic. Get to know them, make friends with them. This one was loaned to me by the bird lady here in Muncie, where I film. And he's a loner bird. Okay.
Next up, we're given the equation natural log of 2y equals xy, and we want to find the derivative and the second derivative in terms of x and y. Let me get that on the screen there for you. What is that piece of formula? That's kind of like the idea apply d over dx twice. So that's just the Leibniz notation for the second derivative. That's what we were calling f prime prime earlier in the course. That's just the second derivative. Okay, first we need to find the first derivative, and we do it by implicit and differentiation. So we're just going to take the derivative with respect to x of both sides of the given equation, like so. All right. What happens on the left-hand side? The outside function is natural log. And we know that the derivative of natural log is just 1 over the entry. So if we think of that entry as some new variable like u, the derivative of the natural log will just be 1 over u. Next we need to multiply by the derivative of 2y, the inside function. Well, that's 2 times the derivative of y. The derivative of y is not just 1, but it's dy dx. Remember, y depends on x, and we need to find its derivative with respect to x. So that was the chain rule right here. On the right-hand side, we need to use the product rule. So the derivative of the first function, x, that's just 1. So we'll multiply it by the second function, y. And then we need to add the first function times the derivative of the second function. So there, that's the product rule that I've used. Okay, what can we do? Well, this is all being multiplied, so notice that the 2's cancel. That's nice. Let's cancel those 2's. And then we're going to gather the dy dx terms all together in order to solve for them. So let's see. I'm going to put the dy by dx terms, the derivative terms, on the left-hand side. We have a 1 over y coming from this, because we canceled the 2. And then when we move that one over to the left-hand side, we'll have a minus x. That's all equal to y. So that means that the derivative of y with respect to x, we can solve for it by dividing both sides of this equation by 1 over y minus x, like so. And, you know, that's not the worst expression, but we can simplify it. Let's do so. I'm going to combine terms here so that everything is a fraction over y in the denominator, like that. So we get 1 minus xy divided by y in the denominator. And then simplifying further, we'll get that the derivative is y squared over 1 minus xy. That's a little more reasonable. Let's leave it that way. Okay, so we found the first derivative. Now we need to find the second derivative. To find the second derivative, we're just going to apply the derivative operator again. We're just going to take the derivative of this entire equation, both sides of this equation. So on the left-hand side, if we take the derivative again, then by definition, we get the second derivative. Okay? You can think of that second derivative as a symbol. It's sort of like if you had d by dx, and then you applied d by dx twice, like that, to y. That's literally what this means. Then, you know, in terms of like the symbols, it's sort of like you have 2 d's, you have 2 dx's. And that's why people write that second derivative in terms of a squaring like that. It's just notation. All right, that's the left-hand side, and now we need to take the derivative with respect to x of this fraction, y squared over 1 minus xy. Okay, now to take that derivative, we need to use the quotient rule. All right, it's a fraction of 2 functions, so we'll need to take the quotient rule. First of all, we have the derivative of the top. That would be 2y, but then multiplied by dy by dx, because of the chain rule. Remember, y depends on x, and we're taking the derivative with respect to x. So that was the derivative of the top times the bottom, minus, and now we'll have the top times the derivative of the bottom. And you know what? I'm running out of room here, so if you don't mind, I'm just going to write down the exact same thing down below so that it'll actually fit. Where was I? We're taking the derivative of y squared over 1 minus xy using the quotient rule. The derivative of y squared is 2y dy by dx by the chain rule, and that's being multiplied by the bottom function. I'm using the quotient rule here, formula for the quotient rule, and then we subtract the top function times the derivative of the bottom function. What's the derivative of the bottom function, 1 minus xy? Well, when we take the derivative of 1, that's just a constant, that'll be 0, so we need to take the derivative of minus xy. And actually, you know what? We already took the derivative of xy before using the product rule. So I'm just going to write down the opposite of that formula. When we do the derivative of the first function, x, we'll get a 1. So we have minus y, and then we have minus x times the derivative of the second function, which would be dy dx. So that's the derivative of 1 minus xy using the product rule. That's all divided by the bottom squared via the quotient rule. We're not done yet. What we need to do next is simplify, but also we need to get rid of the dy by dx's, right? In the problem, we're supposed to find the second derivative in terms of x and y, so we can't just leave it in terms of dy by dx. But check it out. We just found a formula for dy by dx. There it is. So what I'm going to do is I'm going to sub in that formula for dy by dx down below. Here's what I mean. Instead of writing dy by dx, I'm going to sub in y squared over 1 minus xy. So nothing else changed. I'm just subbing in for dy by dx. Over here, let's multiply through and simplify a bit. So we'll have a plus y cubed. Two wrongs make a right. We have minus y squared times minus y. That's just y cubed. And then we also have plus y squared x times dy dx. What's dy dx? Well, again, we just figured it out. It's y squared divided by 1 minus xy. So those substitutions do it for us. And now there you have it. That is the derivative. That is the second derivative. Okay? It doesn't look so nice, so I'm going to simplify a bit, but we could just leave it like that. How can we simplify this formula for the second derivative that we found? Well, up here in the numerator, the 1 minus xy and the 1 minus xy cancel. That's pretty nice. And then when we do that, we'll have a 2y cubed left, and that adds on to the y cubed. So altogether we'll have 3y cubed, right, coming from all these terms. 2y times y squared, that's 2y cubed, adding on another y cubed, we have 3y cubed. And now I'm going to put that over 1 minus xy squared, but I'm actually going to split this fraction up. All right, check it out. These terms that I just addressed, they live over 1 minus xy squared. That's fine. There's only one other term, and it has a 1 minus xy in the denominator. So I'm going to bring that extra 1 minus xy and multiply it by the denominator. I have 3 copies of it there. So that term will have a 1 minus xy cubed. What's left? We have an x, and we have y squared times y squared. Let's write that as x times y to the 4th. So that's a nicer way to write the second derivative. I like it much better that way.
Maybe there lives a happy little bush right along here. We've been doing this show now for well over 11 years. 11 years. And you've made me feel very special to invite me into your home and to let me be part of your family. Thank you very much.